Hello, welcome to lecture 6. So in the previous lecture we saw that the absolute acceleration of a particle or of a fluid element V is given by its relative so this is the sorry this is the absolute velocity is given by the relative velocity minus omega times y, where omega is the rotation rate of the frame, and this can also be expressed as sorry this one u, and the v is expressed as v plus omega x. So this is what we discussed in the last class. So the absolute velocity is the relative velocity plus some extra terms due to the acceleration of the frame itself, that is because the frame is rotating, plus of the frame of reference. So now we'll calculate similarly the way we had calculated the velocities. We'll calculate the double derivatives. So calculate the second derivatives. D square x by dt squared is equal to d squared capital X by dt squared cos omega t plus d squared y by dt squared sin omega t. There's a long expression. This will go into the next slide, so it's better I start again in the next slide. So I'll write it again. So d square x by dt squared is equal to d squared capital X by dt squared cos omega t plus d squared capital Y by dt squared sin omega t plus 2 omega minus dx by dt sin omega t plus d capital Y by dt cos omega t minus omega squared capital X cos omega t plus capital Y sin omega t. Now you will realize because we know what are these variables, so this is nothing but small v, this is nothing but small x. Similarly, we will write the expression for d squared y by dt squared minus d square x by dt squared sin omega t plus d squared capital Y by dt squared cos omega t minus 2 omega. So it will be clear soon why we are doing writing this the expressions in these forms. So minus omega squared minus x sine omega t plus capital Y cos omega t. Again, you will realize by definitions that we had, this is equal to u and this is equal to small y. This one is capital V. I made a mistake there. So this is capital V. This comes from the earlier decomposition that we had. So capital V, small x, capital U, small y, and these are the double derivatives of the uh, coordinates with respect to the rotating frame of reference. When you are measuring the position with respect to the rotating frame. Now, this is expressed in terms of relative and absolute accelerations. So we have named these components of the acceleration in a relative frame of reference as A and B in the I cap and J cap direction, and this is how the acceleration is in the relative frame of reference. The absolute acceleration, capital A, is d squared capital X by dt squared please note the difference of the small I cap, small j cap, and capital I cap and capital J cap here. So these are capital I cap, capital J cap. Here this is capital small I cap, small j cap, and small x, small y, capital X, capital Y. Now this one, you can expand this as d squared capital X by dt squared cos omega t plus d squared capital Y dt squared sine omega t small I cap, because this is what the relationship the we had derived the relationship between the small I cap and the capital J cap, capital I cap, and the small j cap and the capital K cap. So this is what we have substituted, and then this, and the next term is d squared capital Y by dt squared cos omega t plus d squared capital X, sorry, this is minus d squared capital X by dt squared sine omega t j cap. So this is what the expressions look like, because you can substitute the expression for capital I cap and capital J cap in terms of small I cap and small j cap. Now let these be represented as capital I capital A small I cap plus capital B small j cap. So similarly, how we have done it for the first case, the relative acceleration, and this is the absolute acceleration. This is how we have written down. A and B are unknowns. So now from the above we can write small a equal to capital A plus 2 omega capital V minus omega squared x, and small b equal to capital B minus 2 omega u minus omega squared y. So using expressions for capital U and V, so this is small v, so these are the relationship between capital A and small a in terms of both the capital velocities, I mean the absolute velocities and the relative velocities. So here now the reason why we are doing all of these is that we now see these interesting contributions, now differences. Now what we see here from these expressions is that the difference between the absolute and the relative acceleration consists of two contributions. So these are the new terms that you see here. These are the new terms that you see. So these new terms are arising and they are given, I mean they are differentiating between the absolute acceleration and the relative acceleration. It is the acceleration in the rotating frame to acceleration in a acceleration with respect to an inertial frame of reference. So here we see that these new terms so consist of two contributions. So first, so one is proportional. So one is proportional to gamma, this omega, omega times the relative, this proportional to omega times the relative velocity. This is called, this will keep coming back to us and this is very important for us to remember, and this is called the Coriolis acceleration. We'll go deeper into Coriolis acceleration in the next few lectures, but this is called the Coriolis acceleration. This is named after Gaspard Gustave de Coriolis, who was a French mathematician and engineer and a scientist who played a pioneering role in understanding in formulating the motion in a rotating frame of reference. And the second term, which is in this violet here, is the one proportional to omega squared times the coordinate. So these are the terms that we are talking about. and these are called the centrifugal accelerations. So these are the two terms which are arising because which are arising in the new in the absolute when you transform the acceleration based on the inertial frame of reference, you get these two new terms, which are the Coriolis acceleration and the centrifugal acceleration. So the total acceleration, that is the acceleration of the particle with respect to an inertial frame, or the absolute acceleration, is not just the acceleration of the particle with respect to the rotating frame of reference. This is also has two new terms which have arisen here, as you can see here, the Coriolis and the centrifugal acceleration. And this is because the particle, I mean the frame itself is rotating, so to take into account that effect we have to introduce, I mean these two terms naturally appear when you are calculating the absolute acceleration or the acceleration with respect to a stationary inertial frame of reference. So now all of these above can be written in vector form. So with all the derivations that we have done in vector form, we can write the velocities, the absolute velocity, which is capital U, is equal to small u plus omega cross r. If you recall, omega is the angular velocity in which the angular velocity of the rotating frame of reference, and small r is the coordinate, is the location of a certain element, certain particle in that rotating frame of reference. And capital A, that is the absolute acceleration, is equal to the relative acceleration, that is the acceleration of the particle or the fluid element in the rotating frame of reference, plus 2 omega cross u plus omega cross r. So in vector form, we see that these are the forms of the absolute acceleration and the absolute velocity, and capital A, of course, represent the absolute accelerations, and capital U represent the absolute velocity. So this is the absolute acceleration, this is the absolute velocity. So we want to write the last term, that is this term here, in terms of the distance from the rotation axis, the axis of rotation. So to do this, so this is the axis of rotation. So this is the axis of rotation, and then this is the point at which we are interested. I mean, this is our position vector r of the point of interest, and this capital R is the position vector, which is, I mean, which is perpendicular to the rotation vector. So this is perpendicular, this is 90 degree. So now we want to write the last term in terms of the perpendicular vector r from the axis of rotation. So this is the axis. So now, as from geometry, of course, as r equal to small r sine theta, omega cross r is equal to mod omega mod r sine theta. This is by definition of the cross product, and omega cross capital R is equal to, again by definition, mod of omega vector r vector sine 90 degrees, because the angle between the omega vector and the capital R vector is 90 degree. This is what is given in the geometry. This is how we have created the capital R vector. Now this is equal to mod omega mod r sine theta. Sine 90 is 1, and we have replaced r as capital R as small r sine theta. So this is same as omega cross r. So omega cross capital R is same as omega cross smaller. This is what we get it from here. Now we go back to the this last term that we're interested in, omega cross r. So omega cross r will be expressed as now omega cross r, and this one is equal to minus omega capital R. So use the product rule for A cross B cross C and verify for yourself that this is what you get, and omega dot omega is just the magnitude of omega. This is minus omega squared r vector. So use this expression, the expression for the expansion for A cross B cross C, apply it to omega cross r. You will see that only this this second term survives, and then this is omega dot omega is equal to minus is equal to omega squared, and there is a negative sign in front. So we have set here omega dot r equal to 0. So this is what we have set here while getting to the final form. So this is the last term of this absolute acceleration. Now previously we had derived, the momentum equation. So if you recall, we had derived the momentum equations, and in the index notation we had written it down as to be something like this. Rho is the density, u are the velocities, p is the pressure, mu is the dynamic viscosity. So this is how we had this is what we had written down for a incompressible Newtonian fluid. So assuming constant viscosity, we can take the viscosity out of this and writing it only in the vector form. Where if you have done intermediate fluid mechanics, you know that this is the kinematic viscosity. This is defined by the ratio of the dynamic viscosity to the density of the fluid. So this is the kinematic viscosity. So in vectorial form, this is the form of the momentum balance, and this um, we mentioned that this is called the Navier-Stokes equations. So here, I mean, is the vector form. So in a rotating frame of reference, now because we have done, we have seen how the momentum, how the accelerations now change because the frame of reference itself is now moving, which is of applicable, I mean, which is applicable to geophysical flows because we are standing on Earth and we are measuring certain quantities in the ocean or the atmosphere, and the frame of reference itself is now rotating. So now to account for that rotation of the frame of reference itself, we had derived the way that absolute acceleration or the absolute velocities can be represented in terms of the relative velocities and relative accelerations. And we saw that in the acceleration term there are two new terms that appear, which are the Coriolis acceleration and the centrifugal accelerations. Now we'll see how the momentum equation um, will be modified, because we are now in a rotating frame of reference and we'll routinely encounter this modified form of the momentum equation, because multiple such problems that we deal with will be dealing with will be based on measurements of geophysical flows or quantities which are large enough to be affected by Earth's rotation. And because we are measuring from our viewpoint, that is, we are moving along with the Earth, the frame of reference is non-inertial. Hence, those the Coriolis acceleration and the centrifugal accelerations will appear. However, centrifugal acceleration is negligible in terms in most flows of our interest. But before that, I mean, just writing it down, all the steps. So in a rotating frame, the momentum equation is modified into this form. This is the modified form of the momentum equation in a rotating frame of reference. So here velocities, so the u velocities are measured in the rotating frame of references. I mean, all of these quantities are being measured from the rotating frame. That is, for example, we are measuring something in the ocean or the atmosphere, and the velocities u, small u, are the ones which are represented in the rotating frame of reference. And we are of course moving with this, we have an angular velocity omega, because the Earth is rotating. So omega square r term, so this omega square r term is conventionally included in the acceleration due to gravity, in the gravity term g. So in the acceleration due to gravity, it's commonly included. So, and this term, the centrifugal force, the centrifugal acceleration, can also be written as a gradient of a scalar potential. It can also be written as a gradient of a scalar potential. So the equipotential surface, so The equipotential surface corresponding to the potential that includes both gravitational acceleration and omega squared r is called the geoid. So this is a term that we have defined for the first term. This is the equipotential surface corresponding to the potential that includes both the gravitational acceleration and the centrifugal acceleration. So we have said the centrifugal acceleration is conventionally included in the gravity term, and we have done that, and we can express it as a gradient of a scalar potential, and the equipotential surface, which is the surface at which that scalar potential is constant, is called the geoid. So the total gravitational force is perpendicular to it. Force is perpendicular to it. So the perpendicular to this geoid.